right, hello everyone. Today is July 6th. We're going to be continuing on with chapter 12. We left off on slide 38, so if you can go to slide 39, that's where I'm going to start. So I just had a question regarding like when are the due dates? So the due dates can be found on the Achieve website itself. Blackboard doesn't tell you, when the homework assignments are, but if you click the individual homework assignment, like for instance, chapter 12, you'll see that I forgot. We'll get to the homework today, but I always have the homework due after we do it. So the homework will never be due. So if we don't complete the homework today and I had the homework due today, I would just push the homework due date till the day that we completed it. So you'll at least have, let's just say you're listening asynchronously, and I know we have a lot of students listening asynchronously. So let's just say, for instance, we completed the homework today. It could be due today at 11:59 p.m., but I always post the homework assignment due dates on the Achieve website. So if you go to the individual homework assignment, you should be able to see when the homework is due. And I'll show you that to you when we get there. So let's go to, we're on slide 39. I'm gonna bring up my pen. Where is that pen? Okay, so we talked about yesterday, lithium aluminum hydride and sodium borohydride. They're good. They provide good sources of hydrogen or hydrides. So it says lithium aluminum hydride is strong enough to also reduce esters. And here that ester is right here, and carboxylic acids, whereas sodium borohydride is generally not. And they go through the mechanism on the next slide, where that lithium aluminum hydride, you can just think of it as just a hydrogen with 2 electrons, comes in here, it pushes that electron up. Then the electrons on the oxygen come back down to form a double bond that pushes this methoxide off. Another hydride comes in. We have a proton transfer. You can see then we get the alcohol. So it says methoxide is not a good leaving group, but acts like one here because a high energy intermediate becomes a stable aldehyde. So that's what's going on there. So then they come to this thing called diols, and they're just basically, they're alkanes and they have 2 alcohol groups on them. It's just some type of alkyl group is what I should say, with 2 alcohol groups on them. So diols are named using the same method as alcohols, except the E is not dropped from the alkane name and the suffix diol is used. And they have some examples. 1,3-propane diol, so 1, 2, 3, 1, 2, 3, 4, 5, 1,5-hexane diol. Here's ethylene glycol. So they just give you some different names. And ethylene glycol is a common name. And ethylene glycol was made from ethylene. Here's your ethylene. It forms an ethylene oxide, and then it forms something like this. And then another OH comes in here. And it moves it, and that's how we get this ethylene glycol. That's just the common name. So diols can be prepared from the reduction of diketones, and they give you some examples here of how that is done.
Could you go back to the previous slide?
Yeah, this one.
Yeah, is that second example, is that labeled correctly? With the counting of the carbon, should it go the other way?
Oh, sorry about that. Yeah. 1, 2, 3, 4. I apologize for that. I missed this one right over here. I don't know what I was thinking, but yeah, I missed that one. So it should go the other way. So then, this slide just shows you different examples of how you can, the reduction of the diketones. It says recall it. So these methods that they're talking about here, these were from chapter 8. Remember, we can have the anti-addition with the dehydroxylation using these sets of conditions here. We can have the syn dehydroxylation using the catalytic ozone tetraoxide, where it puts it on the same side. So that's from chapter 8. All right, so then they go into this thing called a Grignard reagent. So Grignard reagents are often used in the synthesis of alcohols. To form a Grignard, an alkyl halide is treated with a magnesium metal, and we can see that. So we're going to put that magnesium right here, and then we're going to have a good carbanion, and we can go, then what you're going to have is something like this, and it can go attack right here. It'll move the electrons. You can see how, then you can protonate it, and then you'll get an alcohol. And just shows you right here, electronegativity difference they talk about is great enough that the bond has significant ionic character. So the carbon behaves like a carbanion and is a strong nucleophile, and we talked about that on the previous slide. It can also act as a strong base. So that means it can take a proton. So here you're seeing it act as a carbanion, proton transfer, and we form the alcohol right here. It says the key difference is it does form a new carbon-carbon bond, which you can see right here. That R comes in there, and that R can be anything. It could be a long alkyl, it could be a benzyl group, so it's just saying it's a Grignard reagent, then you have a proton transfer to form the alcohol. But it could also act as a base, show it on the next slide, or if we have water here, we could take that proton there. And here's where that talks about right here. So because the Grignard is both a strong base and a strong nucleophile, it says care must be taken to protect it from exposure to water or alcohol. So if you expose it to water or alcohols, you could, lose your Grignard reagent. Here they're showing you different examples of the use of Grignard reagents. Here they just have a methyl group. So you can imagine that methyl group coming in here and pushing those electrons, and then the proton transfer. Same thing right here. If you have excess, then you can, get rid of this methoxide right here. So what will happen is you'll have that come in first, it'll come up, and then you're gonna have it come back down, you'll have a leaving group right there. And then to get to the alcohol, you just have that second one come in here, just to come up, and then it protonate itself. And then we end up with this compounds here, right? Someone put something in the chat. So that's a good question. It depends on what the question asks for. If they want the major product, please just show the major product. If they want the minor, show the major. Sometimes we're asked to show all the products. So it really depends on the question. You'll see as we go through the homework kind of what they expect. Now on this top right one, it says a racemic product. So obviously, you're going to get an R and you're going to get an S. So it all depends what the achieve homework, wants as far as needing the correct solution. And they're pretty specific about what their needs are. So it says consider the reaction below. We form this Grignard reagent right here. The magnesium would insert itself right there, and we have a good carbanion. You can see then how we can create that reaction, and we just protonate. So the alcohol can act as an acid. So Grignard reagents and alcohols are incompatible. The alcohol can be protected to prevent it from reacting. So they add protecting groups to it, is what they're going to talk about on the next slide. So there's a three-step process required to achieve the desired overall synthesis: protect the alcohol, perform the Grignard reaction, then deprotect it. So they put some type of protecting group on here. In this case, they're going to use trimethylsilyl. It's just one example of a protecting group. So the TMS protection step requires the presence of a base to neutralize the HCl byproduct. So they do show that base right there. We put that protecting group on. So once we have the protecting group on, then it says evidence suggests that the substitution at the silicon atom occurs by an SN2 mechanism, because silicon is much larger than carbon. You get out your periodic table, you'll see that. It is more open to backside attack. It says the TMS group can later be removed with some type of acid or fluoride. TBAF is often used to supply fluoride ions. So tetrabutyl ammonium fluoride. Once we do that, so the overall process, they show this now. So you're going to protect your group. You form your Grignard reagent. You put it right here. Then you have some type of carbanion. You do your reaction. Then you deprotect it, using your TBAF, and you get the desired product that you want. So this all depends on what you want to synthesize. So it says 2 million tons of phenol are produced industrially yearly. So it's a big process. Acetone is a useful byproduct. We've seen acetone in nail polish remover and other products. It says phenol is a precursor in many chemical synthesis, such as pharmaceuticals, polymers, adhesives, and food preservatives. And phenol, remember, is the benzene group with the alcohol on it. So it says tertiary alcohols are converted to alkyl halides with HX but via SN1 reaction. So if it's an SN1, that means it's a stepwise reaction. We have to create a good leaving group. So here we have the loss of a leaving group, which is our water. Then we form a tertiary carbocation. Then we have a nucleophilic attack. And that's for tertiary alcohols. It says for primary or secondary alcohols, reaction occurs by SN2. Remember, SN2 is a concerted reaction where everything happens at the same time. So here we have our leaving group and our attacking group all happening at once. So this is your concerted reaction right here. At first you had to create a proton transfer to create a leaving group, but then we had our concerted reaction. So both the tertiary and the primary or secondary involve a proton transfer. It's just one, it just depends, this will be SN1, the other one will be SN2. This to make an alkyl chloride, zinc chloride must be used with HCl. The zinc cation is required to make the OH a better leaving group. So here it's a better leaving group, they're saying. This is a nucleophilic attack on a Lewis acid. Remember, a Lewis acid is electron acceptor, so that zinc chloride is accepting electrons. And then we have an SN2 reaction. And we form our alkyl chloride right here. Then it goes on to state that you can make, it says recall that the OH group, the alcohol group, can be converted into a good leaving group, such as a tosyl group. Remember, that would be a better leaving group. So a tosylate can then undergo an SN2 substitution to attain an alkyl halide. And we get both the R and the S in this case. So primary and secondary alcohols can be converted to alkyl halides. Let me show you that. And the next slide, they go over the mechanism of how this is done. They say, okay, this is the SOCl2 mechanism. They said this is a bad leaving group, so let's create a good leaving group. These electrons from this alcohol group will go to the sulfur. Then the double bond will go up to the electrons from the S oxygen double bond will go up to the oxygen. Chlorine's a good leaving group. There's a proton transfer right here through this base. And now we have an excellent leaving group, and we can create our alkyl halide right there. So we converted our alcohol to an alkyl halide. And we call SO2 as a gas, so this is going to gas off. So it's not going to go in the reverse direction then. So that's with SOCl2. And then if we look at the PBr3, we have, a good Lewis acid right here. We create a good leaving group then. This bromine comes in, SN2 reaction, concerted. And then we have our alkyl bromide. So it says, this is from chapter 7, we saw that alcohols can undergo elimination in acidic conditions. So just refer back to chapter 7 for that mechanism. The tertiary followed an SN1 mechanism under these conditions right here. So our loss of our leaving group, that's why it's an SN1. Stepwise reaction. Then we have the proton transfer. So we have a proton transfer followed by the loss of a leaving group. That's why we have an SN1. That would be the rate determining step. Then our proton transfer, we're eliminating that proton. And we're forming the alkene. And then it says, recall that E1 elimination generally favors the more substituted alkene. So this is our major product because it's the more substituted alkene. If we consider this right here, we have R, R, R. We just have a hydrogen. Here we have an R group, and we have 2 hydrogens. So we see we have 3 R groups, so it's the more substituted. So it's going to favor that one. But it said the less substituted alkene could only be favored by E2 elimination using a strong bulky base. So if you used a bulky base, it wouldn't be able to come in here and take off these hydrogens as readily. So therefore, it would come and get one from this one right here. It would form the minor product then, which would become then the major product. So remember, you're going to add that one. You're going to protonate that. It's going to become a good leaving group. You're going to have a base come in. It's going to take off. Now, if you use a bulky base, this bulky base will come here, and then it'll go by E2. This would be the bulky base then. Then it says if the alcohol is converted to a better leaving group, we put this tosyl group on there, it's a better leaving group, then a strong base can be used to promote E2. So instead of doing the E1, then we're going to do the E2 because we have a better leaving group. You can just imagine, if you had that tosylate group, it would be a better leaving group. So it says we saw how alcohols can be formed by the reduction. So the reverse process is oxidation. So we have from an alcohol to a ketone is oxidation, from a ketone to an alcohol is reduction. And we went over how to calculate the oxidation numbers yesterday. If you recall, this carbon right here, this would be 1, 2, so it'd be +2. Let me see this one. This one have 1, 2, 3, 4. So it'd be 0. And oxidation is loss of electrons, reduction is gain of electrons. The question is, how is it 0? Because you have to treat each of these as, when you look at oxidation number, it's different than formal charge. You have to treat it as an ionic bond. So if there's carbons here, they're each going to take 1 electron. This carbon then will take 1 of these electrons they'll get 1 from this. There's 2 electrons per the bond, right? So 1 of them is going to go to each carbon. So that's why I'm showing 2. This oxygen is going to take both of these electrons, so you don't have to concern yourself about that. And this carbon is going to take 2 of these electrons from the hydrogen. So carbon should be 4. If you count the electrons around carbon, it's 4 minus 4, and that equals 0. Yeah, I guess you can, yeah, that's right. So Alice is saying, so basically we're taking the electrons from the alpha carbon and then subtracting the additional electrons from the other atoms. And that's what we're doing. We're looking at oxidation number. You can imagine here, none of these electrons are going to be shared by the carbon here. But there's 2 electrons here and 2 electrons here. Well, this carbon's going to take 1. This carbon's going to take 1. This carbon's going to get 2. So it's 4 minus 2. And that's how I got plus 2. So oxidation of primary alcohols proceeds to an aldehyde and then to a carboxylic acid. So here we're showing it going from a primary alcohol to an aldehyde to a carboxylic acid. This is oxidation of secondary alcohols produce a ketone. So we go from a secondary alcohol to a ketone right here. If you count the oxidation numbers, you'll find that, this one's being oxidized and these are being oxidized as well. And it says tertiary alcohols generally do not undergo oxidation because they do not have any protons at the alpha position. So if we look at this as the alpha position, there's no hydrogens right here. That doesn't exist. So there's going to be no reaction. And then what we talk about next is how do you do this? So there is a large number of oxidizing agents that can be used to oxidize an alcohol. It says the most common oxidizing agent is chromic acid, and they show it to you right here. Well, I guess chromic acid is right here. It's formed from either chromium trioxide or, this other compound, sodium dichromate. Chromic acid is, I've worked around it. It's nothing really to play around with. It's very nasty. And it's very toxic. So you can see how we are. So oxidation of the alcohol with chromic acid involves 1, the formation of the chromate ester, and then 2, the elimination to form the pi bond. So we're forming the chromate ester right here. Usually we think of an ester like this, but this is the chromate ester because we have chromium here. Then we take that chromium ester and we eliminate it through an E2 reaction. So we have elimination. And we form our ketone. So to do this, you'd have to pronate this, right? I could even take one from here. It'd be depronated. It comes here, and this is a leaving group. But I said this is fast and reversible, though. Then that water will depronate it through E2. The chromic acid will oxidize a primary alcohol to a carboxylic acid. So anytime you see a primary alcohol and you see chromic acid, you have a this chromic will oxidize to a carboxylic acid. We see that right here. Here's your carboxylic acid group. So went from an alcohol to a carboxylic acid. Then it says pyridinium chlorochromate can be used as an oxidant to produce an aldehyde. We see that right here. We'll just, abbreviate it PCC. So we're taking a primary alcohol to an aldehyde. This one was used to take a primary alcohol to a carboxylic acid, whereas this one is taking a primary alcohol to an aldehyde. So the question is, does PCC work with only primary alcohols? So it does work with secondary alcohols too. But if we use a secondary alcohol, then we're going to make the ketone. And then that's a good point. So the next slide, it says, regardless of the oxidant used, either chromic acid or PCC will convert a secondary alcohol to a ketone. So we can use it to make secondary alcohols into ketones. Well, if you have a primary alcohol, then you have to recall that we're only going to make the alcohol with a PCC, and chromic acid is going to take a primary alcohol to the carboxylic acid. So since chromium reagents are toxic and horrible for the environment, alternatives have been developed, and they cover two of them in this chapter. They have the Swern oxidation, where you see that dimethyl sulfoxide, DMSO, and the oxyl chloride form the active oxidant. And this can be used then to convert secondary alcohols to ketones. So the chlorodimethyl sulfonium ion, the active oxidant, is attacked by the alcohol, and the trimethyl amide facilitates elimination to form the pi bond. So we have the triethylamine, we can form the pi bond. And ultimately what we're going to form is this ketone right here. So we get a secondary alcohol, we convert that to a ketone. And we can use the same conditions to convert the primary alcohol to an aldehyde. So we convert the secondary alcohol to a ketone. If we do this on a primary alcohol, we get our aldehyde. Hey guys, I'm gonna be right back. I need to shut my car windows real quick. I think it's gonna rain where I'm at, so just give me a minute. So if you're in the Berea area, you're getting a nice shower right now. So it says like PCC, the Swern oxidation converts primary alcohols to aldehydes. So we have our primary alcohol and we're converting it to an aldehyde. So they have this other alternative, DMP, Martin periodine, yields an analogous results as a Swerin oxidation. It converts a primary alcohol into an aldehyde and a secondary alcohol into a ketone. So it says DMP oxidation is believed to proceed through a periodone intermediate, and they show that right here. It says DMP oxidation is non-acidic and doesn't require high temperatures, but chromium oxidations do, so that'd be another reason to avoid the chromium oxidation. And they give you this example and they say, you know, kind of predict what would happen if you added chromic acid to this. So we have a secondary alcohol here, primary alcohol. We had an aldehyde. So you're going to convert this into a carboxylic acid. This will be formed a ketone right here. You know, get the carboxylic acid right here. And they show you a good, they show you everything I showed on the next slide. So you convert those secondary alcohol, we'll go to a ketone, and the primary alcohol and the aldehyde goes to the carboxylic acid. So nature employs reducing and oxidizing agents. They're generally complex and selective. So NADH is one such reducing agent. This is the reactive site of NADH acts as a hydride delivery agent. So you can see that hydride delivery agent right here. Forms a hydride and come in and attack that ketone. And then we get the alcohol. And, you know, if we have NAD plus, you know, that can act as an oxidant and it can undergo the reverse process. And it shows that on the next slide. So NADH and NAD plus has an interconversion and plays a key role in metabolism. And it says, recall that tertiary alcohols do not undergo oxidation because they lack an alpha proton, but you can on a phenol, even though it doesn't have any alpha proton. So you might expect a phenol to be similarly unreactive, but it says in reality, phenols are even more readily oxidized than primary secondary alcohols. And it shows that on the next slide. So it says phenols oxidize to form benzoquinone, which in turn can be reduced to hydroquinone. So here are benzoquinone right here, and we can further reduce it to hydroquinone. It says quinones interconvert with hydroquinones, which are a key process in cellular respiration. So ubiquinones act to catalyze the conversion of oxygen into water and are found in all cells in nature. So just showing you some different compounds that you might find in nature. Ubiquinone catalysts. Again, these are biomolecular reactions shown right here. And it says recall that reactions fall into the category of either changing the carbon skeleton or changing a functional group. This was from an earlier chapter where they talked about H2 and Lindlar's catalyst that converts this triple bond to a double bond. We could have just used this to go from here to here. But to go from the double bond to a single bond, to use H2 and the platinum. And they show you how to go in the reverse order too. So at the end of the chapter, they kind of just have a review of the different situations that can arise. It says now that we have reactions that interconvert primary alcohols with aldehydes and secondary alcohols with ketones, you have a bunch of synthesis that you have in your back pocket. So it says these 6 functional groups can be grouped by oxidation state. And then they go over some strategies, which we're going to see in our homework. So it says recall that Grignard reagents can act to form carbon-carbon bond forming reactions, and we saw that, or we formed some type of carbanion since it has a lot of ionic character. We protonate that, we get the alcohol, and they just show you if you use excess, you can get rid of this. And then they say there's no one reaction that converts an aldehyde into a ketone. With a Grignard reaction followed by oxidation, it can be accomplished in 2. So you attack this with a Grignard. And we follow that by an oxidation, and we get our ketone. And they give you the conditions to form that ketone right there. All right, so that's the end of chapter 12. Let's take our 10-minute break now. We'll come back and we'll start with the homework. So enjoy your break, and I'll see you in 10 minutes. All right, everyone, I hope you enjoyed your break. So we're going to move on to the chapter 12 homework slides. Question 1. It says, what is the IUPAC name for the compound shown? So we have this compound, and we're going to call that, so at the 2 position, that'll be 2-butanol. I'm going to keep it on the same slide because question 1 and 2 are pretty much the same. So if this is your first time using Achieve, I'll stop here for a couple minutes because it's your first time using it. There's an adjustment period to getting used to it as far as inputting the as far as drawing the structures. Maybe not so much spelling it out, but drawing it there is. Question 2. We have this compound here. It says, what is the IUPAC name? Well, we have a cyclohexane group with an alcohol, so it's cyclohexanol. In question 3, we can keep it on the same slide. It's just it says, what is the proper IUPAC name? You're going to select 2,2-dibromocyclopropanol. So we have questions 1 through 3 done. Question 4. I guess we could keep it on the same slide. Question 4, you're only going to select valid hydrogen bonding when you see an H bonded to another oxygen, so that's valid. It doesn't have it in this case, but it could also be to a nitrogen or to a fluorine, but they don't show that. It's invalid when you see another hydrogen bonded to another hydrogen, or this, well, not that, it'd be this. So these will be, valid if it has an H to an O, invalid if it's 2 H's or 2 O's. So go ahead and select those options. And we'll go to question 5. We'll use a new slide. So we're going to rank these from the most acidic to the least acidic. So we'll have the most, this would be H2F plus, then followed by CH3SH2 plus, followed by CH3 2OH plus, and followed by CH3OH. This will be the least. So you could always look this up in a textbook as far as like knowing the pKa values, and that's what I highly recommend doing. This one is pretty, I shouldn't say pretty obvious, but this one, you know, right here, there's no charges on this one. So this one will have the least amount of acidity. Here we have a charge right here. But I would go ahead and look this up in a reference book. And whoever has the lowest pKa, so what you're going to do is look for the lowest pKa, and that's going to be the most acidic. So if you find the one with the highest pKa, that's going to be the least acidic. So question 6. They give us a compound. They give us this here. And they give us this OH group, and they say consider an SN1 and an SN2, right? So that's a good point that she brought up. If you look at the electronegativity increases this way. So there's a few different ways to look at this. If you look in the textbook, that's a for sure way, and you can also look at the electronegativity. Fluorine would be the most electronegative. So for question 6, it says they want SN1 or SN2. So if we're going to do the SN2 one, that's going to be the easier one. We just have this coming here, and this comes here. It's all concerted. So then our SN2 product will be this right here.